Hello. In this video, we build on our geometry skills from last time, points, lines, and rays, to describe a new type of two-dimensional shape called a polygon. Let's get started. So when we describe a polygon, we're talking about a closed figure, so not an open figure. For example, if I had a ray and another ray here, and that was it, just two rays, notice that's still open, right? But if I closed that picture with a third ray, now this is called a closed figure. So that's what we mean by a closed figure here. Okay, so if we have a closed figure that's determined by three or more line segments, as we just noticed, there need to be at least three line segments, we say that this is called a polygon. Now the word polygon comes from actually the prefix poly and the suffix gon. Okay, poly means many. In this case, we're typically talking about a three or more, so 3 gon, 4 gon, 5 gon, etc. And then gon means angle, so it's the number of interior angles that we have in this closed figure. So sometimes, just for convenience, we'll use the word n-gon, meaning a 3 gon. N represents the number of angles, 3, 4 gon, etc. So notice, though, if we have the same exact length for each of those sides of the polygon, and if every single interior angle is also the same measure, we would note that this would be called a regular polygon. So regular polygons are very special, and we'll talk more about them in future slides. But for now, let's notice the very most common types of polygons to memorize. The first one is our 3-gon, also known as a triangle, right? 3 angles. Now, there's many types of triangles, and we'll study them in this class. But for now, the 3-gon is a triangle. A 4-gon, okay, doesn't necessarily have to be a square. It could be a rectangle. It could be any type of quadrilateral. A square is just one type of them, so just keep that in mind. It doesn't have to be a square to be a 4-gon, but that would be a regular quadrilateral, right? Because it would have exactly the same measures. A 5-gon is called a pentagon. A 6-gon is a hexagon. A 7-gon is a heptagon. An 8-gon is an octagon. A 9-gon is a nonagon. A 10-gon is a decagon. An 11-gon is a hendecagon. And a 12-gon is a dodecagon. They start to sound a little bit more like dinosaur names as you get into higher and higher n values there. Now, in general, if I know I have a polygon and I want to determine the sum, so that means adding up all of the angles inside of the polygon, that would be known as the sum of your interior angles. In other words, in this picture, angle 1 plus angle 2 plus angle 3. If I add up those measurements, what should I get? Okay? Now, you may already know that for a triangle, those 3 angles add up to 180 degrees. And you may already know that if you add a 90, a 90, a 90, and a 90 from this right angle situation with our rectangular square, special quadrilaterals, 90 times 4 is 360 degrees. So what do you think would happen if I took an angle, 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 angle? So basically 5 angles inside of a polygon. So that's a pentagon. What do you think that would create? If the pattern was 180, 360, what do you think's happening here? If you guessed we're going to add another 180, you'd be correct, right? So if you add another 180, you get your 540 there, right? And then you can keep going with that. So what is going on here? Well, you're basically adding on another triangle, if you will. So if you had added a triangle to your rectangle or your square or your quadrilateral, you would get another 180 degrees. And that's what happens with each new additional interior angle for each polygon. So the formula here is, how many triangles do you have? Well, in the triangle itself, we just had one triangle, right? So that's one copy of 180 degrees. But in the quadrilateral, notice you could actually cut that in half, and you have 2 triangles inside. Well, 2 copies of 180 degrees is 360. And you could actually cut this into 3 triangles here, and you could cut this into 4 triangles, 5 triangles. I encourage you to try it on your own. It's kind of fun. And what you notice is the number of triangles that you have contained within each pentagon will always be 2 less than the n value. So the n value is how many interior angles for the polygon, okay? So in the case of a triangle, you did 3 minus 2. That's the number of copies of 180 we have. In other words, 1 copy of 180. In the case of the pentagon, you would do 5 minus 2, because there's 5 interior angles, times 180. And that would give you 3 times 180, or 540. So you can easily calculate the sum of the interior angles of a polygon using this formula, n minus 2 times 180 degrees. So 2 less than whatever n is, that's how many triangles can fit inside. Where n is, again, the number of sides of the polygon or the number of interior angles. Okay, make sure that formula is committed to memory or that you can rederive it if you need to as you work through problems like we're going to see in the examples that follow. Example 1, can we find the interior angle measure of each angle of a regular octagon? So both of those words are important. Octagon is our actual noun here. That is what we're talking about. We're talking about when n equals what? That's right, n equals 8. Okay, that's an octagon, like a stop sign. Now, the reason I can say like a stop sign and be accurate here is because it adds the adjective regular. So when we talk about the adjective regular for a polygon, that means every single side has the same length and every single interior angle has the same measure. So that is what you see with the stop sign, right? All 8 sides of that stop sign, exactly the same length, and all 8 interior angles, exactly the same length as well. So with that in mind, how would I calculate the angle measure if I was going to make my own stop sign perfectly using a protractor and some cutting tools? What would I need to do? Well, I'd first need to know what is the length of each side and what is the interior angle. More importantly, what is the interior angle so that I can get the right shape and then I can blow it up or shrink it as needed. So in this case, I noticed that since n is 8, the sum of the interior angles should be 8 minus 2. That's how many copies of 180 degrees we have. In other words, that's how many triangles should fit into an octagon. So there should be 6 of them. 6 times 180. And when I multiply that out, 6 copies of 180, what do we get? Did you get 1080? I hope so. And what happens if you divide? So that's the sum, right? That's the sum of the interior angles. Now, because we see the word regular here, that's very important. Because of that adjective, that means that all of the interior angles have the same measure. How many of them are there? There's 8. So how could I find out each individual one if you know the total is 1080, but you need to cut it into 8 pieces that all have the same amount? You do division, wouldn't you? That's right. So you would take 1080 and you would divide it by the number of actual angles, not by 6, and that goes into the formula for the sum, but by the number of angles that we need to create, right? So dividing by 8 in this case. And that should give you your answer of 135. And to verify that, you could check if the rotation makes sense. If I rotate 135 all 8 times, do I get 1080? Okay. And then you would have the ability to make an octagon that is regular. Okay. So that is how you can use your information of what type of polygon you're dealing with, along with knowing that it's regular. You take that information together, and then you could use your tools to actually create a perfect octagon measuring 135 degrees at each rotation. Okay, so make sure you have all of those fun facts for each type of polygon on a note card handy for when you're doing your homework. Okay. Well, on the next slide, we want to talk about the different types of triangles, which are thrigons, right? And what makes them special or unique. Okay. So first off, we have probably one of the most fun types of triangles, and you'll actually be able to watch a fun video if you look at your interactive notes. There's a nice video there about how equilateral triangles in particular are helpful in architecture and building. Okay, so check that out if you're curious. But for equilateral triangles, what we're talking about here is triangles where all 3 sides have exactly the same measure, right? Exactly the same measure. What that also means is all 3 angles have the same angle measure as well. Okay, so it's both equilateral, meaning same length, equal length, and it's equiangular, meaning all 3 angles inside have the same angle measure. Okay, so that kind of is an easy one to remember. For example, the angle measure here, if you take 180 degrees and divide by 3, that's going to be 60, 60, and 60, right? Okay, but as far as the actual measurements on each side, depending on how small the equilateral triangle is or how much you want to blow it up, we'll talk more about similar triangles in a few minutes. You might have different dimensions, right? You might have 2 feet by 2 feet by 2 feet, or you might have 100 feet by 100 feet by 100 feet, right? So that varies, but the angle measurements stay the same. All right, so the next one we're going to talk about is isosceles. When we talk about isosceles triangles, some students like to see the 2 S's in the front and remind themselves, that's reminding you that 2 sides, exactly 2 sides, have the same length. 2 sides have the same length. So in this case, it looks like it's this side, because of this tick mark and this tick mark. So these 2 sides are exactly the same. The 3rd side does not have to be the same in order to be isosceles. Okay? But for a scalene, what ends up happening is all 3 sides are different. So there's no equal sides, right? One side is the shortest, another side is the longest, and another side is somewhere in between the short and the long side. Now, why do you need to know all these terms? Because in some word problems, when people are describing things to you in a math problem or in an architecture situation, if there is an object that is a triangular shape and it's described using one of these words, you would want to know what they mean, okay? So when we talk about scalene, again, no sides are the same. Isosceles, exactly two sides are the same. And equilateral, all three sides are the same length. Okay, now let's talk more about the angles for a moment. If you have a triangle that has three angles, which are all less, so with the word all here, make that very clear for us, which are all less than 90 degrees. That means that this is called an acute triangle because they are all acute angles. So maybe this is like 20 degrees, right? And this is another one. Maybe this is a little bit bigger. Maybe this one was more like 70 degrees. Okay, 70 and 20 is 90. Well, then this would have to be 90. So my numbers are a little bit off. But the basic idea is you're going to have all three angles here adding up to 180 still, but they all individually are less than 90. Okay, so these three angles are not the same measurement, but they're all less than 90. On the other hand, you might have a case where two of the angles are less than 90, like in this case. This is acute and this is acute, but is this an acute triangle? No, because here we have a 90-degree angle. So if we have one 90-degree angle, this is not an acute triangle anymore. Instead, it's called a right triangle because it has one angle which is 90 degrees. Now, what do we mean by an obtuse triangle? An obtuse triangle is a triangle that has one angle which is bigger than 90 degrees. And that's what we notice right here. This large angle is obtuse. Now, by default, you can only have one obtuse angle in your triangle because it's bigger than 90. If you had two angles that were bigger than 90, then if you start adding up all three angles, the whole thing will exceed 180, won't it? So you should notice that for an obtuse triangle, only one angle is greater than 90, whereas for an acute triangle above, all three had to be less than 90. And for a right triangle, again, exactly one angle is 90. So let's put those words together. Make sure you have them in your notes or in flashcard form to see if we could draw a right isosceles triangle. Okay, so where would I begin? Well, I know that it's a right angle, so I might take one ray and maybe have it pointing up with its arrow and its endpoint here. And I might take the other ray, because it's a right triangle, and form a 90-degree angle, maybe to the right. You could have also gone to the left, so that I have a nice 90-degree angle. So there's the right part. Now, what makes it an isosceles triangle? Do you remember? You can look in your notes or you can look at the slide. Yeah, exactly two sides have to have the same length. So you would want to get your ruler out and be actually precise about this. I'm eyeballing it here, but that's not actually what you'd want to do. You'd want to measure, okay? And so let's say, for example, that this is 2 units, okay? And then we measure another 2 units going this way. When I connect those two rays and form that 90-degree angle, because those two are the same measurement, I'll get another color here. How about brown? And connect my third line segment to form my triangle. Now we have a right isosceles triangle because 2 of the sides are the same length and we have the right triangle. So that would be one way you could do it. Again, it could have been 4 and 4, 6 and 6, 100 and 100, as long as 2 sides are exactly the same length. You have taken care of the isosceles part. Next up, we see the words an acute equilateral triangle. An acute equilateral triangle. What does this mean? Well, it means every single one of our angles inside has to be less than 90, and this triangle has to be equilateral, like we saw here, right? Where we have all 3 sides at the same length. So we could just draw a triangle literally just like the one above, where all 3 sides appear to look the same, and we can tell the reader that using our tick marks here, that we're trying to draw a situation where all 3 sides are the same length, okay? And notice here that we would say each of these angles interior must be less than 90, so this is why we are acute. If any one of them had a box, a little square in the corner, that would indicate a right triangle, which no longer would satisfy the word acute for the triangle. Finally, the last picture here, they would like us to create a scalene obtuse triangle. A scalene obtuse triangle. So what does scalene mean? That's right. All 3 sides have different lengths, okay? So again, you can draw that in one of these ways like we have above here, scalene. but we want to make sure that we have an obtuse angle as well, okay? So that might be the very first thing I might do here. Come this way. I might draw a ray, let's say, going to the right, okay? Maybe it's a short little ray. And then I might draw a longer ray. So those are clearly not the same length, right? And then I might draw my third ray that's going to connect them. It's kind of an ugly triangle, but bear with me. All right, so we connected our two rays with our third line segment, and notice we have the situation that they asked for. We have a scalene because maybe this is the shortest, maybe this is the second longest, and this is the longest side, okay? And we have a nice obtuse angle for the reader or the visual person who's looking at this to see, okay? So that would be my attempt at drawing a scalene obtuse triangle. Okay, so again, this will be important, especially when you're talking about word problems or application problems. You need to identify what's the actual picture associated with the words that I see. Okay, so let's see if we can put this to use in our next slide. Now in this slide, we're actually going to talk about how we can take triangles, which are what we call similar triangles, and solve for missing pieces. Now the skills that are required to be successful with this are 1, drawing the right picture, 2, interpreting the picture, and 3, doing a little bit of algebra, so solving a proportion problem in order to identify the missing pieces, okay? So we can solve what we call proportion problems by cross multiplying, and you can check out the video that I've posted there on the actual interactive notes in the slides, and that video goes through more examples that might help you get a better feel for what's going on with similar triangles and with cross multiplying in general. But here I want to first talk about the definition. What do we mean by a similar triangle, okay? So by definition, we're talking about two shapes, in this case triangles, but they could be other objects as well. These two shapes are basically the same shape. What I mean by that is they have all of the exact same inside angles or interior angles, but they're not necessarily the same size, right? So I don't know if you ever heard of a movie called Honey, I Shrunk the Kids, Honey, I Blew Up the Baby. These are movies back in like the 1990s, I think. And the basic idea was that humans got shrunk or they got blown up, right? Same thing with your triangles here. We have a triangle that is then shrunk down to a smaller size or blown up to a bigger size. And we use this all the time in real life. You might not think you do, but even if you take medication, you'd use this type of idea, right? You might have someone who weighs 150 pounds and they take a certain medication. Maybe they take 5 milligrams of a drug, but someone else who weighs 300 pounds might need to take more of the drug. You can set up what we call a proportion problem. Similar things happen with our triangles here. If we're missing sides, we can set up a proportion. So how do we do that? We notice that corresponding angles are equal, okay? So take a look with me at the two triangles that we see here. We see a triangle that has a side that has A here, B here, and C here. So I would call this, for example, triangle ABC. And then over here, we have a triangle that has side R, side P, and side Q, okay? So we could have triangle, in this case, let's see which ones correspond. So let's be real careful here. It looks like to figure out the correspondence, we're gonna look to the actual angles. So notice that Z is here, Y is here, and X is here, okay? So let's see where we can find those corresponding angles, which are equal, right? So angle X is over here, so these two are congruent pairs. Angle Y is here, so these two are congruent pairs. And angle Z is here, so these two are congruent pairs, okay? So basically, in order to determine in this picture which side is congruent to the other side, because corresponding sides have the same ratio, they might be 2 times bigger, 3 times bigger, they might be half the size, a quarter of the size. We have to figure out what that ratio is, okay? And so to do that, what we were going to notice here is angle Y in the first triangle is between A and C, A and C. Angle Y in the second triangle is between P and R, okay? What about angle X? Here it's between B and C, so B and C, angle X. And where is angle X over here? Between R and Q rather, okay? Between R and Q. So with that in mind, you might draw something like R and Q, or Q and R, might be better to go in alphabetical order with us. So let's do that, Q and R, okay? And maybe put the P in front, and let's see if that makes sense. Well, let's see where angle Z was again. Angle Z was between A and B, and here angle Z is between P and Q. Here's A and B, here's P and Q. So we're in the same place. So as far as naming is concerned, we have one triangle ABC and another triangle PQR where A, B, and C are related to P, Q, and R, respectively, okay? So what we're saying here is A is to P, and that's what we're writing here. Do you see that? A over P. A is to P as B is to Q as C is to R, meaning those ratios need to be preserved. We don't know yet. Is A twice as big as P? Is it is P twice as big as A? We don't know yet. We have to figure this out. But once we know the relationship between one of those pairs, we know the ratio between the other ones as well. So let's put this to use in our picture here. Notice what we have in this picture. It says we can solve for x in the figure below. And what I see here, I don't know if you see it as well, I see that I have a right triangle, triangle ABC here. So triangle ABC in my picture here looks like this. It's a nice small right triangle. Now, is this a right scalene triangle? Is this a right equilateral triangle? Is this a right isosceles triangle? Or is it just a right triangle? Well, in this case, it's telling me that from B to C, that segment is 6 units long, and from A to B, that segment is 10 units long. So could this be isosceles? Are those two the same? No, so this is not isosceles. Could this be scalene? Are all 3 sides different? Yeah, it appears that this is a scalene triangle. So we have a nice scalene right triangle, ABC. Okay, now because I have this 90-degree angle here, and because I noticed that angle A is also inside of this bigger triangle, it does appear that we're going to have 2 similar triangles. And let's see if we can visualize them. What is our bigger triangle? Well, it looks like it's not just A to C, but it's also A to E, and it's not just A to B, but it's also A to D, and then out here it's also E to D, forming our 90. So this bigger triangle would be triangle A, and instead of B we go to D, so this is AD, and instead of C, where do we go? We go to E, right? ADE. And let's see if that makes sense. Is A, this length here, 10, is that going to correspond to our A in our picture? AD, so from not just A to B, but A to D. Yeah, that would correspond down here. So this is our A, this is our D, and then up here is our E. So AD is corresponding with AB. So these two are corresponding with each other, that side, right? Now, do we know the total length from A to D in this case? Well, yeah. If I take 10 plus 10, what do I get? I get 20. So I have that length known to me. I also know from D to E is x units. Okay, we don't know what x is yet, but we do know it's x units. And notice that E to D, that segment, corresponds with C to B. So C to B, E to D, those are corresponding sides. And what's another corresponding side? How about from, in the first picture, we had ABC. So let me write that out for you, ABC. That's a B. We had from A to C. Here we have A to E, right? Now, did we know what A to C was? No, they didn't give that to me, nor do we know what A to E is, okay? So sometimes we'll have to solve for that, and we might have the Pythagorean theorem, which we'll study in a future video, that could be helpful. But in this case, do we even need to know those 2 sides to find x? Not really, right? Because once we realize that angle A here is the same as angle A here, those are corresponding angles, so they're congruent. Angle B here is the same as angle D here, they're both 90. And since one is inside of the other, by definition, angles C and angle E are also congruent to each other. So this is a case of one triangle being blown up, right? It's the same basic shape, all the corresponding sides are proportional, and all the corresponding angles are congruent. But the ratio of their sides is what we need to find in order to find the unknowns, okay? So in order to do that, let's find a proportion problem that is buried in our picture here. So for our smaller triangle ABC, I could say that we know that side AB is 10 units. So here's our smaller triangle. And that side AB is proportional to side AD. And we can also see it from the way I wrote the triangle here, AB to AD, right? So 10 is to 20. And then we write our equal sign when we build our proportion problem. And then for our bigger triangle here, what do we know about the bigger triangle? Well, we're looking for ED. the side from E to D. And here we have the side from C to B or B to C is known as 6. So we're going to start with our smaller one here. And so we start with our smaller one up top here, which was 6, and our bigger one was at the bottom here. So we're putting the bigger ones at the bottom and the smaller ones on top. So 6 is to what? X. So we have to set up our proportion in a way that makes sense. If you do small on top, big on the bottom, then you need to do small on top, big on the bottom for the other one as well. Let me make that a different color so that's more clear to you. So for the big, that was the 20 and the X. For the small, that was the 10 and the 6. So that is the order that we're following here. You have to do it that way? No, you could have done big to small, small to big, as long as we are consistent. Same thing works with medication dosages or anything that you're scaling up or scaling down. Now the actual math behind it, once you've set it up, is pretty easy. We're going to do what we call cross multiplying here. So we're going to cross across the equal sign. We're going to go along the diagonal. 10 times x is 10x equals 20 times 6, which is 120. Okay? And when I do that, I now have a simple linear equation to solve by undoing multiplication with division. So divide both sides by 10. To get x by itself, we should be getting that x is equal to 12. So now we know that this side is equal to 12 units. Now, was that way more work than needed if you could just tell that one is twice as big as the other? No, yeah, you're right. You did not have to do all that work this time. But in reality, most of the time you're going to have nastier numbers, so it's important to understand the process of how to set up a proportion problem describing a smaller similar triangle and a larger similar triangle, or in general, if you're talking about medications and dosages. When you're scaling something up and down, proportion problems are your friend. Okay, again, feel free to check out that video that I posted in the interactive notes. I think that might be helpful. All right, for our last slide together, we need to learn a few more definitions, but this time we're going to take a break from triangles that were 3-gon and focus on quadrilaterals, which are our special 4-gons. So again, when we're talking about a quadrilateral, we're talking about a 4-gon. Okay. So I have a fun little saying here that you might want to put in your notes. It kind of trips some of my students up, so let's see if it bothers you. Every square is a blank, but not every rectangle is a blank. Every square is a rectangle, but not every rectangle is a square. Really? Well, yes, that is the case. But let's talk about why. So let's talk about some definitions. So if we look at my little flow chart here, what we're talking about on this entire slide are different types of quadrilaterals. So what is the definition for a quadrilateral? It's just a 4-gon. So it is a polygon with 4 sides. So here I've just drawn or it's been drawn for us, a nice funky quadrilateral. When I say funky, I mean there aren't necessarily any parallel sides, right? We have a side going one way, a side going another way. They're kind of just all around doing their own thing. Different lengths, right? All 4 look very different here. So this is an example of kind of a wonky looking quadrilateral. There's no regularity to it, right? There's no nice symmetry to it. So this is just a random quadrilateral. But when we're talking about quadrilaterals, we could have some more definition to make them more special and unique, okay? So one type of special quadrilateral is called, a subcategory here, the kite. When we're talking about the kite, not necessarily the ones you fly, but geometrically speaking, we have a nice degree of symmetry here. You notice that we could actually draw a nice vertical line up and down, and you'd have a mirror image on both sides of that kite. And similarly, if you were to draw another line here connecting this diagonal here and cut it in half, you could have nice little shapes on both sides that are the same, okay? So what is the definition formally of a kite? It basically is a quadrilateral that has 2 pairs of adjacent congruent segments. So this segment here is congruent to this segment, and they're adjacent at this vertex, right? Whereas this segment here is congruent to this segment, and they are adjacent at that vertex. Okay, so they're not parallel, but they are adjacent pairs which are congruent. Okay, now a special type of kite, if we want another subcategory, is a rhombus. Okay, so does a rhombus fit that definition? Well, yes, you have an adjacent pair here with the same length, right? And another adjacent pair here with the same length, okay? So you got congruent sides, 2 pairs of congruent sides. However, the reason this is a rhombus, not just a regular kite, but a special kite called a rhombus, is because all 4 sides have exactly the same measure. So it is a regular in that sense. It is a regular quadrilateral. It has all four sides of the same length as well. Okay. And another special type of rhombus, okay, which also is a kite, right? So we're kind of building our way through the subcategories here, would be a square, because notice that a square, yes, these are all 90, but we have a pair here of adjacent congruent segments and another pair of adjacent congruent segments. So that is another example. What makes a square a special rhombus, however, is that each of the four angles is 90. So all are right angles. So you have to have all four being right angles in addition to having them be congruent. Okay, so it's not just a rhombus, it's not just a kite, it's a special quadrilateral, it's a special rhombus, and it's a special kite. So squares are pretty powerful. We'll talk more about them in a moment. Let's head over to another subcategory of quadrilateral called a parallelogram. Well, just like the name suggests, we are going to have some parallel line segments. So what do we mean by a parallelogram? We mean a quadrilateral that has exactly two pairs. So two pairs which are parallel. Okay, so for example, this side is parallel to this side. And additionally, this side is parallel to that side. So they both have to be parallel to one another in order to be a parallelogram. Now, a special type of parallelogram, we'll continue on this train again, is a rectangle. Really? A rectangle is a parallelogram? Well, yes. Do you notice that this front part, or top part rather, this top segment, is parallel to this side, meaning that they never touch because they have the same slope? And similarly, on the left and right, these two sides, they're going to also be parallel with one another. They also, if you were to extend them out forever, they would never cross because they have the same slope. So what makes a rectangle special? Why is it not just called a parallelogram then? The only difference between a regular parallelogram and a special one called a rectangle is that in addition to having two pairs of parallel sides, you also notice that in every corner of this parallelogram, you have a 90-degree angle, okay? And while we're speaking of rectangles, there is a special rectangle known as a square. Really? So a square is also a rectangle? Yes, by definition, because it is a parallelogram, two pairs of parallel sides. We see that here, parallel to parallel, parallel to parallel. So two pairs of parallel sides, right? As well as the fact that in every corner is a 90-degree angle. So by definition, every square is a rectangle, but not every rectangle is a square. Why? Because remember, to be a rectangle, you don't have to have every side to be the same. It doesn't have to be regular in that sense. Okay, it doesn't have to be the same length, but you just have to have the 90-degree angles in the corners. All right, let's head over to our last category of special types of quadrilaterals to finish off our slide here. And that would be a trapezoid. Now, if you are studying this in a different country, like using British curriculum, they'll typically call this a trapezium. So if you've heard that before, it's the same thing. A trapezoid and trapezium, they're interchangeable. All right, so what do we mean by trapezoid? Well, with trapezoids, we just have one pair of parallel lines, segments. Okay, just one pair. So exactly one, to be quite honest. So notice here we have on the top line segment, that is parallel to the bottom line segment. It could have been the other way. We could have rotated this. So as long as there's exactly one pair of parallel sides, whereas the other two are not parallel. And how do you know that? Well, if you were to extend them out, they would intersect each other since they have different slopes. So we have exactly one pair of parallel sides. This is called a trapezoid or a trapezium. And we'll have different formulas in our future lessons to talk about how to get the area, let's say, of this two-dimensional object. So you have to make sure you understand which type of object you have before you can start doing calculations. You might be thinking, I would never need to know this. Not necessarily. What if you're putting some tile floor down and there are some interesting shapes? If you recognize a trapezoid or a parallelogram of different types, this might be helpful for you to calculate your area that you're going to need to cover your floor or to paint a room, something like this, okay? All right, the last type of special quadrilaterals that we see under the trapezoid category is an isosceles trapezoid. Now, why is it called an isosceles trapezoid, not just a regular old trapezoid? Well, to be a trapezoid just requires that you have one pair of parallel sides, and we have that here, top and bottom. So the other two are not parallel. But when we say isosceles, what we're saying here is that two of the sides have the same measurement, right? Just like with our triangle. Two sides have the same measure. Two sides have the same measure. If that is the case, that's an isosceles trapezoid. Just like with a triangle, it was isosceles if two sides had the same length. Similarly for a trapezoid, if two sides had the same length and it's a trapezoid, we'd call it an isosceles trapezoid. Okay, so that is a lot of definitions. I highly recommend flashcards or some other device that you could use to memorize the different types of definitions with the different types of polygons. So after you've done that, happy practicing, because math is not a spectator sport. I'll see you next time.